Welcome to ATMOS 5000, Day 30. Our objectives are being pulled from Chapter 8, Section 8.1. And specifically, we're going to be looking at absorption bands and windows, looking at the transmittance of radiation through the atmosphere. We'll revisit blackbody radiance using the Planck radiation law, and we'll use that to determine the brightness temperature of objects and show how to do that. And then lastly, we will introduce the concept of weighting functions, which basically are used by satellites to determine what altitudes the satellites are most sensitive to in terms of the passive radiation that they are receiving. So let's start off by looking at windows in the electromagnetic spectrum. So here we have figure 8.3 from Stull, and on the y-axis we have the transmittance. So this is the ability of the atmosphere to transmit the radiation. So when the transmittance is 100%, then the atmosphere is essentially transparent and all of the radiation is making it through. In contrast, when the transmittance is 0%, then none of the radiation is making it through the atmosphere and it's all being scattered and or absorbed. So the way we define this is we have a window when the transmittance is 100%. We have areas, of course, where the transmittance is equal to 0, and those are opaque regions. Those are not useful for remote sensing. And then we have a shoulder region where we have a dramatic change in the transmittance with wavelength. And as the wavelength in this case changes, it dramatically changes the transmittance through the atmosphere. And then we have what's called a dirty window, which is a wavelength range where the transmittance is somewhere between 0 and 100%, but not changing rapidly. And from a satellite perspective, the focusing in on the shoulders and the dirty windows are areas where you can actually use to diagnose information about the atmosphere. You can't do that if the atmosphere is completely transparent at a given level, and you can't do that if the atmosphere is completely opaque at a level. But if you're in the shoulder region or in a dirty window region, then you can get information about the atmosphere at that altitude. So let's take a look at the atmospheric window, essentially for shortwave radiation. So here, once again, we have the transmittance on the y-axis and the wavelength on the x-axis. And way on the far left, we're basically looking at the near ultraviolet, the ultraviolet UVA, UVB, and UVC. Then we have the visible light, and then we have the near infrared. So just due to molecular scattering, there is 0% transmittance through the atmosphere at wavelengths of shorter than 0.3 micrometers. So that's the dashed line on this graph. It's called the molecular scattering. And so that's essentially defining the maximum amount of radiation that could be transmitted through the atmosphere because of the effect of molecular scattering. So let's just take, for example, at a wavelength of 0.5 micrometers, which is green light, the maximum amount of transmittance that we could get through the atmosphere is about 35%. And the brownish tan line shows what the actual transmittance is through the atmosphere. And in that region of visible light, essentially from 0.4 up to 0.7, the transmittance through the atmosphere is basically the theoretical maximum, with the exception of course, of molecular scattering. There is a window where you have the maximum amount of transmittance possible in the visible wavelengths. And then when you move into the near infrared, there are places where the atmosphere is much more opaque, and there are specific absorption lines, primarily water in the atmosphere has absorption lines that will absorb a lot of the near infrared at particular wavelengths. So the atmosphere is almost opaque at about between 1.35 and 1.4 micrometers. But there are bands in there when the atmosphere is essentially transparent to near infrared as well. That would be windows. There are several windows. There's a nice big window between about 1.2 and 1.3. There's another window between about 0.9 and 0.97. Excuse me, that was 0.85 to 0.87 and 1 to 1.1. Next, we'll look at continuing into the near infrared and moving a little bit towards the far infrared. And so if you look at the transmittance is no longer limited by scattering. So you could theoretically have 100% transmittance. Well, very close anyway. And so this includes the information on the UV and the visible. It's just compressed way down on the left-hand side of the chart now. So you can see the really strong absorption bands of water at about 1.7 and, excuse me, about 1.7 and 1.4-ish micrometers. And then we have an atmospheric window from 2 to 2.5. And then we have an opaque region due to carbon dioxide and water from 2.5 to 2.8. We've got essentially a dirty window that includes methane, absorption by methane and water. And then we have a window between about 3.5 and 4.2, and followed by another opaque region. And then we have many, many absorption lines, which are very thin for water vapor in the 4.75 to 5.5 micrometers. If we look at the far infrared, we have a very large window, essentially extending from about 8.5 micrometers all the way up to about 13 to 13.5 micrometers. We actually refer to this as the atmospheric window. This happens to be the wavelength range for the maximum emission of radiation from the Earth, and the atmosphere is largely transparent to this infrared radiation that is emitted by the Earth. If that were not the case, then the Earth would be much warmer than it currently is. But right in the middle of this atmospheric window is a pretty strong absorption band for ozone. And so if we were to increase ozone concentrations in the atmosphere, then we would increase the absorptivity and reduce the transmittance inside the atmospheric window. The upper portion of this atmospheric window, that shoulder region, is controlled by the carbon dioxide concentration. If we increase the carbon dioxide concentration in the atmosphere, which is what we're doing, then we will actually be increasing the absorption in the atmosphere and decreasing the transmittance in that range there between about 13 to 14 micrometers. And by increasing the CO2 concentration, you actually close down the transmittance through the atmospheric window slightly, allowing for more heat energy to be retained in the Earth's system. And that is one of the primary reasons, the physical reason why increasing carbon dioxide concentration will lead to climate change. On the lower end of the atmospheric window, we have methane and nitrous oxide, N2O. And if we increase concentrations of those greenhouse gases, then we would also start to close the atmospheric window in that shoulder region. So here you can see how these specific greenhouse gases have an impact on the amount of radiation which we are allowed to send to space through the atmospheric window. So if we look at microwave radiation, so now we're looking at wavelengths in terms of centimeters. So the transmittance for the atmosphere above 1 centimeter is very high, but there are specific absorption bands, primarily by water and diatomic oxygen. And down at the bottom, you'll see we have radar bands. We have the Ka, the Ku, the X, C, S, L, and P. We'll be learning about these different wavelength bands that are used for radar, but you'll notice that these bands are conveniently located in areas where the microwave transmittance is very high. So the atmosphere is not opaque to these wavelengths, which means that you can actually send these microwaves out and they will not be attenuated by the atmosphere itself. So that's a good choice for using a remote device. So as you recall, the Planck radiation distribution is one of the blackbody radiation laws. And we had this B lambda is a function of temperature. This is the Boltzmann distribution, Planck distribution essentially. And it shows how the emission of radiation changes as a function of wavelength and temperature for a black body. And the summary diagram of this equation is shown down at the bottom, where it shows that as the temperature increases, the amount of energy emitted by an object increases dramatically, but the peak in the distribution also shifts towards shorter wavelengths. And so if you know the temperature, the radiating temperature of an object, then you will know the amount of radiation that it's giving off at each wavelength, or at least if it were to behave as a black body. So we can use that information to estimate what we call the brightness temperature of an object. And the brightness temperature is essentially the Planck radiation distribution solved for temperature and instead of the irradiance. And so in this case, you have L lambda, which is the measured radiance in watts per meter squared per steradian, and you still have the same constant C1 and C2. And now you essentially are able to solve this equation, and if you know the distribution, what the distribution looks like, you can actually fit it to a brightness temperature. And I'll give you an example of that now. So here we have the spectral irradiance, basically watts per meter squared per nanometer, and the radiation at the top of the Earth's atmosphere is shown in yellow. So that is the amount of radiation as a function of wavelength that's being received at the top of the Earth's atmosphere. The only way to deduce that is essentially from satellite observations, because you can't do that on the ground. Because the atmosphere absorbs different types of radiation differently, and so you'll end up with a very different radiation distribution at sea level, which is shown in the blue. So because of that scattering and absorption within the Earth's atmosphere, the amount of radiation received at the sea level is reduced in some cases by not much, but at other wavelength bands significantly reduced. For example, no radiation below about 300 nanometers, which is in the ultraviolet, actually makes it to the surface, even though that is those wavelengths are available at the top of the Earth's atmosphere. So back to our brightness temperature. So we have the amount of radiation, the radiation distribution coming from the sun in yellow, and we have superimposed on that the blackbody radiation curve from Planck's distribution, and we could plot that up for different temperatures. And what we're trying to do is find the best match between the actual measured radiation at the top of the atmosphere and the temperature that would provide a curve that fits the measured data. And as it turns out, the best fit for the solar radiation data is a temperature of 5,800 Kelvin. So what we're actually saying there is that the brightness temperature of the sun is actually 5,800 Kelvin. It's because that gives us the blackbody spectrum that best matches the shape of the spectrum that we receive here at the top of the Earth's atmosphere. So if we have a satellite in orbit and it's looking down and trying to measure the amount of radiation that is coming from the atmosphere or from clouds or from the ground, uh, this is called a passive radiometer. And what it's doing is actually just collecting radiation of a certain wavelength. But what we need to know is we need to know where the atmosphere is transparent to that wavelength range and where the atmosphere is opaque. So in the figure to the left, figure A, we have the transmittance ranging from 0 to 1 as a function of altitude z for a particular atmosphere. It's a kind of a hypothetical situation. So this atmosphere has a zero transmittance between 0 and 5 kilometers, which means that none of that radiation is essentially able to make it through the atmosphere. And then we also have a transmittance of 1 above 10 kilometers. And so there's nothing in the atmosphere to absorb those wavelengths at those altitudes. The interesting region is between 5 and 10 kilometers, where the transmittance of the atmosphere changes. In this case, it changes in a linear manner. And it goes from essentially being completely absorbed to being completely transmitted. And it's that region of the atmosphere where a satellite can actually make useful measurements about the atmosphere. If there's nothing in the atmosphere that attenuates it, the radiation, then there's not going to be changes. The radiation is going to remain unaltered from 10 kilometers until the satellite altitude. And obviously, the radiation lower than 5 kilometers is never going to make it to the satellite. But some of the radiation will make it to the satellite between 5 and 10 kilometers. And what we have on the right is what we refer to as the weighting function, which basically shows the altitude at which that passive sensor in space is actually sensitive to. So this particular wavelength, the satellite would only be able to provide information about the concentration of whatever the absorbing species happen to be in the location between 5 and 10 kilometers. So let's look at another hypothetical radiation transfer weighting function. So on the left, we have a different profile of the transmittance, kind of similar to what we had before, but yet shaped slightly different. It still goes from being opaque at low altitudes to being transparent at high altitudes, but instead of changing at a linear clip, it actually changes in this kind of curvy manner, sort of thing. And so what we have is we have a different shaped weighting function in this case. So the peak in the weighting function will happen kind of at the inflection point in the transmittance curve. So then in this case, it happens where the transmittance, the tau, is equal to about 0.5. And it will be sensitive to the atmospheric values a little bit above that and a little bit below that, kind of decreasing significantly on in either side of the maximum sensitivity altitude. So let's take a look at the weighting functions from a current GO-16 geostationary satellite. So they have many different radiometers on the GO-16 satellite. They have 16 channels, so they're basically measuring the passive radiation in each of these wavelength ranges. So channel 1 is a visible channel in the blue, which is the 0.45 to 0.49 micrometer radius, all the way up through red, which is going to be channel 2, the 0.59 to 0.69, and then you kind of get into longer and longer wavelengths. So we're primarily, the first two channels are the visible radiation, and everything else is looking at infrared radiation. So over on the left, we actually have the weighting functions for several of these channels, and it basically indicates, where that transmittance is changing rapidly in the Earth's atmosphere. So for channel 8, which is a wavelength centered at 6.19 micrometers, it's actually sensitive to water vapor, and because water vapor has some absorption in that wavelength range. But the weighting function is such that it's going to be sensitive to water vapor in that range between about 4 to 14 kilometers. But the peak sensitivity is going to be at an altitude of about 7 or 8 kilometers. And so we refer to channel 8 as a high tropospheric water vapor channel. Channel 9 has a similar shape, but is, instead of having a peak in the weighting function at 7 or 8 kilometers, has a peak at about 6 kilometers. And it's also sensitive to water vapor in the atmosphere, and we'll refer to channel 9 as the mid-tropospheric water vapor channel. And likewise, channel 10 is also sensitive to water vapor in the atmosphere, and the weighting function indicates that it's going to be most sensitive to water vapor below 5 kilometers, and so we refer to that as the low tropospheric water vapor channel. And you can see that the shape of all of those, 8, 9, 10, are essentially the same, but they're focusing in on different altitudes. So you can get water vapor information about different layers in the atmosphere. We'll compare that with like channel 12, which is an ozone channel. The atmosphere is basically transparent because there's not much ozone between about 5 and 15 kilometers. The ozone concentrations are really low. If we do have higher ozone concentrations, it's in the lower part of the atmosphere, down near the surface, and up in the stratosphere. And you can see that the channel 12, which is sensitive to the ozone concentration, right in the middle of the atmospheric window, if you recall, is sensitive, in fact, to the low-level elevation, or the low-level ozone, and the stratospheric ozone as well. And then channel 13 is looking at surface and cloud infrared in the middle of the atmospheric window, and it's going to be most sensitive to the emissions from the surface and from warmer clouds at the lower part of the atmosphere, because the atmosphere is largely transparent to that. So let's check that. It's going to be sensitive to the surface and the cloud, essentially infrared energy emitted by the cloud top, regardless of the elevation of the cloud, because the atmosphere is transparent to those wavelengths. So whatever is being emitted from the surface below will make it to space. And so channel 13 is looking at surface temperatures and cloud top temperatures. So you can see that by exploiting different regions of the the electromagnetic spectrum, and looking at places where you have windows and where you have shoulders, you can actually devise instrumentation that is sensitive to getting information and data about certain gases in the atmosphere at certain elevations. And by constructing this very carefully and using a suite of instruments, you can actually put this together to get a lot of information about the atmosphere at different layers, even though you're using a passive remote sensing device such as a satellite.